23, let's take a look at that one. What was 23? Does anyone have that problem? What was 23? Zero to 1 dx over? Oh, right. Okay. So we're actually, let's come back. I was going to do one something similar to this as an example, and we'll come back to this one. Okay? Yeah. So this is the right one to ask about, and we'll come back to that. So let's look at this example before we do that one. Let's look at this example. Okay, so we've learned this technique. We're gonna go through these several techniques of some harder antiderivatives. And what is so important about antiderivatives? So it's going to be very mechanical, lots of algebra, but we don't want to lose sight of why is it so important that we can generate lots of antiderivatives. What work do they do for us, antiderivatives? Does anybody pick up in the first week the importance of antiderivatives? Yeah. Okay, right. So they would allow us to find an amount of accumulation or a change in amount, right? Given rates. So right here, suppose this is from 10 to 32. So we're integrating from 10 to 32, 3x plus 7 over x squared plus 16. And what is the meaning of that? So can you tell the person next to you, and with all the detail, that whole expression there means something as a whole. What does it mean as a whole, and what are the details behind that? Go, tell the person next to you. Go. Okay. So a volunteer, so first of all, as a whole, so that whole thing as one expression in a nutshell means what? Or gives what? Robert. Okay. Okay, yeah, it's the accumulation of some quantity. It's accumulation of some quantity, or the total change, or the net change in some quantity. Okay, and so then here are the details behind that. So what net change is it? What net change is it? So the 10 to 32 is as x changes from 10 to 32, right? So we have this one quantity x is going to change from 10 to 32, and some other quantity is going to have a net change of this amount, right, as x changes from 10 to 32. And what's the last detail of this? One more important detail here. Yeah, so the net change of the quantity that we're going to find here has this as its rate of change function. 3x plus 7 over x squared plus 16 is the rate of change function. Okay, so what, I'm going to put a box, what does this represent in the red box? In the red box, what does that represent? Yes, sir. And what's that? Okay, and what's that? So that's also the symbols that we use. So he's saying it's like dy, and that's right. And what is dy? What kind of change? Yep. A little bit of change, right? And the integral then means we're going to sum up like a gazillion of those little changes, right? So this is representing one little itty bitty change in that quantity, and then this means sum up all those changes. And so what's in the red box is constant rate of change. It's our meaning for constant rate of change. That a little change in dependent is found by the rate times a little change in independent. That's why we spent half a class period on constant rate of change, because it's the foundational principle in integral. Okay? M dx, right? M dx. And then the DOI is a little bit of change found by constant rate of change. Okay, so all that. To go back to our question, why antiderivative? So we got the meaning of this, that it's a net change of some quantity, but now we want to find that net change. How are we going to find that net change? Well, we have a different way to express this net change. And now what's that other way to express that net change? Right, so it's going to be, we know that we can define it as final value of a quantity minus initial value of the quantity, right? Final minus initial. So to get a net change, two ways to do it. Sum up a bunch of little changes, or just take the final value of the quantity minus the initial. They both give you that net change. And so then this is what we'll be able to calculate if we had f, and capital F is? The quantity function, which is the antiderivative of our rate function, right? It's the antiderivative. That's why antiderivatives, we're going to spend all this time generating lots of antiderivatives, because they do the work for us that we'll be able to calculate this net change that we have when we get an integral like that. Okay, so now we're working on this 3x plus 7 or x squared plus 16, and we're thinking about what function will have that as its derivative. And so our first question we'll always ask is it undoing the chain rule? So can we have some kind of function that's just, by doing the chain rule, do we get that? Can we use undoing the chain rule, or is there a function such that if we did the chain rule, could we get this? What do you think? And if not, could we make a small change to this so that just for our own practice, what small change to this could we make so that, yeah, it would be really exactly the result of a chain rule problem? Factor out the what? There isn't, no, because these are plus, right? These are plus there. You can't factor out 7/16. Yeah. Okay, so make it a product? Is that what you're saying? Is that what you mean? Okay, so 3x plus 7 times x squared plus 16 to the... Okay, so this is rewriting the problem. So again, is there a function whose derivative looks like this that we can recognize easily? And if not, can we make a slight change to this so that that would be true? Okay, so we do the natural log of x squared plus 16. Yeah, so that's what you should be thinking. Something like the natural log of x squared plus 16. So that's our attempt. And remember, do absolute values. Okay, so this is an attempt. And so then what do? We check it. And when we check it, what do we get? 1 over x squared plus 16 times 2x. Okay, is that exactly this? Is it close enough that this attempt, we could adjust this attempt? We got a problem here. What's the problem? Not an extra x. So factors are no problem, right? So this is a 2 and that's a 3. That's no problem. What's the problem? The 7, right? The plus 7. If this plus 7 wasn't here, then we'd be home free. This would be an easy problem, right? We'd just have one, we just have to clean up the mess a little bit. The problem is the 7. So with that 7 there, we should be getting something like 2x plus 7. And that's just not happening. Okay, so this one's a little bit different. So this isn't without the 7, then it's a pretty standard undoing the chain rule problem. That's easy. But with that 7 there, we got difficulty. So this next technique is really common no matter what we're using for antiderivative, and that's we've got this fraction. We've got a sum or difference in the numerator. So what could we do with that? We've got a sum or difference in the numerator. We can split it, right? We can split this up. Thinking about adding fractions, so we could do 3x over x squared plus 16. And we said that one we can do. We just figured out we could do that one. And then what? Plus 7 over x squared plus 16. So remember that when you add fractions, you need a common denominator, and then you just add or subtract the numerators with the common denominator. So here's kind of, we're going backwards, right? So it's like we've got a single fraction, and we're decomposing it into parts. So we know we just found out we could do this. Not so bad. But then we come to this one. So let's finish this one. So we had what? We had natural log of x squared plus 16. So how are we going to adjust that to get it right? Well, we have another factor of 3. We're going to need a 3 here. But then we're also going to need... No, we're just doing this. It has nothing to do with 7. We're just doing this. No? So we imagine, right, so imagine what would happen if we took the derivative. We'd get, what, 2x. So we've got our 3 here, but we don't have a 2. So divide by 2. So what I just did was what the goal is of this undoing the chain rule, that you don't have to do the attempt, take the derivative, and adjust. If you still need to do that, keep practicing that, that's okay. But the reason for that kind of procedure that I taught you was to eventually get to this point where you could kind of reason it through and just write down the answer like that. That's what we want. That's our goal. Okay, so now we come to this other one. So we got that. That's good. Now what about 7 over x squared plus 16? Can we do undoing the chain rule for that one? Can we do undoing the chain rule for that one? No, because we need an x, right? We need that x in the numerator. Does it? It doesn't work, because what we need is what? G prime f of x times what? F prime of x. So we need, if it's going to be undoing the chain rule, we need something that's just like this to start with. We don't have that. We would have it if there was an x up here, because then the rate of change of this interior function here, x squared plus 16, would be essentially x, and we'd have it. But we just have 7. So undoing the chain rule is not going to work for the second one. So we have to recognize what we've got. What does it kind of look like? Yeah, so do you recognize from all the derivatives that we took that what the derivative of inverse tangent is? 1 over 1 plus x squared, right? So it's kind of like that. It's kind of like that. We see the something over x squared plus a constant. So what's the big problem that we have? Is the 7 a problem? 7's not a problem. It's just 7 times 1, right? The 7's no problem. What's the real problem here? The 16, because tangent inverse, the derivative has to have 1 plus x squared. So our big problem here is the 16. So what can we do? We need to make that a 1. How can we make that 16 a 1? So if we took this thing and we divided that by 16, that would make that a 1. That'd be good. But we can't just go around dividing denominators by 16. We'd also have to do what? and divide the numerator by 16. Now we've maintained the equality of what we had before, and we're going to get that 1 in that key spot. So when we do that, we get, so this becomes, what, 7/16, no problem, over 1 plus x squared over 16. Now we're making some progress. Okay, so but what we really have with the derivative of tangent inverse is 1 over 1 plus what? Something squared. Not something squared over a number. So the last thing we need to do is transform this into something squared, and we have it. What's that? So, right, so if it's some function of x squared, it would be, what goes in there? X over 4. And now we're ready to do tangent inverse. So all these are just equal to this, right? So that we're just still working on the rate this part of the rate function, right? So this then is equal to this. And so now we can do a first attempt on that, okay? So our attempt at the rate of the antiderivative would be? So what would you say now for the antiderivative of that? Well, 7/16 times what? Inverse tangent of x over 4. So that could be our first attempt. So if we were to take the derivative of it for our check, would it be exactly this? If we took the derivative, would we get exactly what we started with? Not quite, right? Why? Because when we do the derivative of this, what do we need? So yes, it's going to be 7/16 over 1 plus x over 4 squared. What have we done? No. That's a composite function, so we need chain rule, right? Times 1/4, right? Derivative of x over 4. So we need times 1/4. So then how do we adjust our attempt? We're going to need another factor of 4 in that first attempt so that we don't have the 1/4 if we took the derivative. So now we're ready to write it down here. So this is going to be plus 7/16, but then 7 times 4, right? 7 times 4/16, tangent inverse, sorry, of x over 4. And then if this is an indefinite integral, right, it means all antiderivatives. All antiderivatives. So we need, let's see. And then that 7 times 4, of course, is 28. And then 28 over 16 is, simplify that. Yeah, we shouldn't, so we shouldn't have done that. Instead of multiplying 7 times 4, we should have just said 4 over 16 is what? That's 1/4. So this should be 7/4. 7/4. Okay, so a lot going on in this example. First is, this is something that's going to show up when you have a fraction with sum or difference in the top. A common technique would be to break that up into two fractions. And that first one would be x over x squared plus 16. That's straightforward undoing the chain rule. But then the second one, we have to recognize that it was close to inverse tangent. So then we can adjust, what would we need to do? We need to get a 1. Instead of 16, we needed to get a 1, so we divided top and bottom by 16. And then we needed to get that x squared over 16 to be something squared, so that's x over 4 squared. And then we're ready to do tangent inverse of x over 4. And then we got to clean up the mess with the 1/4, so we need another factor of 4. And in the end, we get that. Lots going on there. Any questions on that example? Do you follow? So now this brings us to the example that you asked about. So again, are we good? So the example that you asked about was 4 minus x squared. So first of all, is it undoing the chain rule? Is it undoing the chain rule? Just straightforward. How would you make a small adjustment? What different problem that's close to this would be undoing the chain rule? Right, so if there was some factor of x, like 3x or just x, right? If there were an x up here, then it would just be undoing the chain rule, and our first attempt would be, what would our first attempt be? No, it's square root, right? It's square root. Just because it's in the denominator doesn't mean it's natural log. It's not to the minus 1. Well, it's to the minus 1/2. So 4 minus x squared to the positive 1/2. That could be our first attempt if we had an x up there. If we had an x up there. But we don't. So, but this would be the first attempt if we had an x up there, and then we could finish it. But we don't. So it can't, it's not immediately, it's not undoing the chain rule. So then we have to recognize, what is it? We have to remember all of our derivatives and ask, which one is this close to? So there was one that has the derivative square root, 1 over square root of 1 minus x squared. And what function's derivative is that? Inverse sine, or arc sine, that's right. So that's what we're going to do, but in order to use the inverse sine as an antiderivative, we need to do what? First, we have to make that 401. And I'll let you take it from there. So see if you can, as per practice, do the math right, get that to be a 1, but then adjust the rest of it so it's still equal to that, right? You can't just change the 4 to a 1. You've got to, do arithmetic so that it becomes a 1, but then the whole expression is equal to that. And then we know we're working towards the antiderivative being some form of inverse sine. So I will let you take it from there to practice that technique. Okay, anybody have a question? So undoing the chain rule is a really common technique. It's kind of like the most important one. It's the one you should always look for first. It shows up the most, and yeah, it just shows up all over the place. So we always want to ask about that one first. Is it undoing the chain rule? Is there some function whose derivative by the chain rule is giving me essentially the rate function that I have? Can I uncover that original function? Okay, so in the next web work that's due Friday, you'll have more. Actually, we'll mix in some more of these undoing the chain rule with the next technique, so you can start practicing identification as well. Okay, so if we give them to you in groups, then you're losing practice on this important thing of you come to an integral, you got to identify what you're going to do in the first place. Okay, so let's move on to the next. Next is undoing the product rule. Undoing the product rules. So first we want to recall, what does the product rule says? It says the derivative of the product of functions is what? The first times the derivative of the second plus the second times the derivative of the first. Remember what it is not. What it is not is this. Derivative of the first times the derivative of the second. Oh, wouldn't it be nice, right? But it's not. So it's not that. Whenever you have the product of two functions, you have to do the first times the derivative of the second plus the second times the derivative of the first. So if we were to now do antiderivative or integral, we'd have this, right? So if I look at the antiderivative of both sides, or piece by piece, I'd have the original function f times g would be the antiderivative of fg prime plus the antiderivative of g f prime. That's logical, right? Follows? So all I'm doing is just basically taking the integral of both sides. When I do that, I just get the original function f times g is integral fg prime plus integral g f prime. So with undoing the product rule, you'll be given just kind of like one of these. Okay? You won't be given a sum of integrals that is like this perfect, like that would be so rigged. If you were given a sum of integrals like that, that would be just entirely rigged, right? So, but what you're really given in these problems is you're just given like one of them. It's kind of like fg prime. And basic rules or undoing the chain rule doesn't apply to this. Okay? So it might look like it because it's a product of two things, but it doesn't, undoing the chain rule doesn't really work. So what we do is we're going to anticipate that that was one of fg prime was one of the terms in the product rule, and we're going to find the other one. We're going to find gf prime, and then look at the antiderivative of that. And if that's easier, if that's doable, then we know we've got the right technique here. Okay? Because then what will our given integral equal? So our given integral will equal just the product of f and g, what? Minus this easier integral. Okay? So here's the strategy. So we're going to be given fg prime, the integral fg prime. We're going to think of that as one of the terms of the product rule, fg prime. So first we're going to determine what f and g are. Determine what f and g are. Compute the product of f and g, and then compute this easier integral, integral gf prime. And so then what does our given problem equal? It's going to equal f times g minus this easier one. So it's like we're really never doing the antiderivative of that. We're doing it indirectly, right? We're doing it indirectly by finding another antiderivative that's easier and doing fg minus that. So does that overall strategy make sense? So this is what you got to keep in mind as you get into the nuts and bolts of taking derivatives and antiderivatives. You keep in mind what you're doing. Okay? You're thinking of it as one term of the product rule. We want to solve the integral of the other term of the product rule because it's easier, and then we're just subtract. So let's look at an example here. Okay, first example is integral 4x cosine x. So first question we always ask, is it undoing the chain rule? Is it undoing the chain rule? So what small change could you make to this so that it would be undoing the chain rule? Just for our own practice here before we get started on this one. What small change or what different problem that's really close to this would be undoing the chain rule? So can you see what change you would make to get that? So this is a really good question to see if you really understand undoing the chain rule or not. So what small change would you make to this so that it would be undoing the chain rule? So you want to change the cosine x this? So he's saying cosine x squared. Okay, so the factors don't really matter though, because we always clean up the factors. What about this? Now would this be undoing the chain rule? Do you see that? And the first attempt would be sine x squared. You should be thinking sine x squared. Sine of x squared. And then we need another 2, right? So then the answer would be 2 sine x squared would be the answer to that problem. That's our goal, to be that fast. To be that fast. So yeah, so the antiderivative of cosine is sine. We take the derivative, we're going to have 2x. Well, we have 4x, so I'm going to need another 2. So 2 sine x squared. Okay? Okay, but that is not what we have. We have this instead. Okay? So we want to think of this problem. We'll try this technique on doing the product rule. Is 4x cosine x, that 4x cosine x, is it one term from the product rule, like f g prime? Okay? And then if so, what is f and g and what is g of f prime? So then the question is then which of these is f and which is g prime? Well, there's only 2 possibilities, so we can just try one, and if it doesn't work, we could try the other way and then see if we can learn something along the way. Okay, so let's just match them up. Let's say f is 4x, and g prime is cosine x. So what are we going to need to complete this? We're going to need g, and we're going to need f prime, right? Because we need f, g, and f prime to do this. So what is f prime? 4. What is g? So this is like a mini antiderivative here. G would be what? Negative sine x or positive? Positive. Okay, so here, this is a possibility, right? That 4x was the f, and that cosine x was the g prime. And then in that case, our f prime would be 4, and our g would be sine x. And so now we're going to write out what this stuff is, right? So we'll just, for simplicity's sake, we're just going to call this a for answer, right? That's what we're trying to. We're trying to get this answer, a. And so then we're going to say plus integral of, what's g? Sine x. F prime is 4. And then f times g would be 4x sine x. So the big question is, did we approach this correctly? Did we pick f and g prime correctly so that this is easy? If this is easy, then we got it. And is this easy? Integral sine x times 4. You better be thinking, yes, that's easy. We like that one. We like that one. So then what is our answer? A is equal to 4x sine x minus this easy one, right? So what is integral sine x times 4? Antiderivative. Yeah. What's that? Because we're solving for this integral, right? This is our 4x cosine x. How are we going to solve for it? By doing this minus this. You see that? So this is the integral now we're solving, which is g f prime, which is sine x times 4. So I'm going to give myself some more room here. I'm going to do it somewhere else. So it's going to be 4x sine x minus. So antiderivative of sine x times 4. 4 cosine x? Negative. And then we're going to need this is indefinite integral, so it's going to be all antiderivatives. So we can simplify that as 4x sine x plus 4 cosine x plus c. And how can we check to see if we're right? take the derivative. We're going to take the derivative of that, and when we take the derivative of that, we should get exactly the rate of change function that we started with. And when we take the derivative of that, what we're going to have, product rule, right? We're going to do the product rule. And then we're going to get something cancel out, and we're going to be left with 4x cosine x. So if we were to take the derivative of this, we would get exactly 4x cosine x. Okay, so the moral is that we guessed it right the first time, right? We guessed it right, that f was indeed the 4x, and the g prime was indeed the cosine x. But here's why that worked. Why did that work? Because by taking the derivative of 4x, we got the power less by 1. So rather than 4x cosine x, we got 4 times sine x. So that's why that worked, because we chose f to be this 1 with the power of x, and it reduced that power of x by 1, and that's why it made this other integral easier. Had we made 4x be the g prime, what would have g been? If we did g prime of x was, what, 4x? Then g would have been 2x squared. And now what we would have had? We would have had something like sine x or cosine x times 2x squared. And that's worse, right? It's worse than what we started with. So that's why we don't want to do that. Okay, questions on this example? Okay, another example. Let's do e to the 3x, x squared. Again, we're thinking of this right here as the e to the 3x, x squared as one term of the product rule. And we're going to, or before we do that, so how about, so we always ask the question, is it undoing the chain rule? Is it undoing the chain rule? Does that work? Okay, so everyone think to yourself, what small change to this integral would have it be a straightforward undoing the chain rule problem? What small change to this would make it be a straightforward undoing the chain rule problem? Okay, so you see our composite function here? We need the x squared to be something of the derivative of this interior function. So it should be 3x cubed. If you're thinking put a cube on there, you're right. That would now make it undoing the chain. Because x squared is essentially the derivative of this plugged in, this interior function. It's not what we have, so we think of maybe undoing the product rule. And we're going to go with this. And so from what we learned in the last example, what might we make f and what might we make g prime? F should be squared, thinking about reducing the power of it, and then g prime, e to the 3x. So that would make f prime 2x and g. So now we got a mini little antiderivative to do here. So remember the e function, it's just the antiderivative of itself, but then we got that 3 there. So it should be times 1/3, right? Times 1/3. So that in itself was like a little teeny undoing the chain rule problem. Do you see that? That little antiderivative. But that's hopefully a real easy one. Okay, so now we're ready to set this up. So this is a plus integral, what's g? 1/3 e to the 3x times f prime equals f times g. X squared times 1/3 e to the 3x. So the big question is this integral easier or doable? easier or doable compared to the first one we had? We got 1/3 e to the 3x times 2x. Can we do that easily? Or is it, I mean, at least, at the very least, is it better? It's better, right? Because instead of x squared, we have x to the first. But it's kind of like we're back where we started with. We're back to the same problem we started with. We still don't have undoing the chain rule. So what do? So now we're trying to get this integral done. Any techniques that we might be able to do to get this integral done? The same one. If we do it again, what's going to happen? That power of x will go down to 0, and then we'll be left with just something e to the 3x, which we'll be able to do. So we're going to do it again. We're going to think of this as its own isolated problem, and we're going to do this same technique again. Okay, so now I'll do that in red. So now we're looking at this one, and we'll call that B. Okay, so in order to do B, we're going to have to pick, we'll call them capitals now, F, G prime, and what should we make F? 2x, G prime should be 1/3 e to the 3x, which makes F prime equal to 2, and G is going to be equal to, we're going to have e to the 3x, and then what's our coefficient going to be? We need another 1/3, so it'd be 1/9. Okay, so B is going to equal capital F times G minus the integral of capital G F prime, which is 2x times 1/9 e to the 3x, not 1/g, 1/9. Oh no, help. Minus integral 1/9 e to the 3x times 2. Which we can do. 2x, 1/9 e to 3x. So we're going to have 2/9, but we're going to need another 1/3 now, right? So this is antiderivative we can do. We'll need another 1/3. So it'll be 2 27ths. And so that whole thing is the answer to this subproblem, which is equal to this. And then what's A was our original problem. A is going to equal the x squared 1/3 e to the 3x minus that. This thing minus B. And that's the final answer. Okay, so you're going to have to reflect on that. We kind of went fast at the end. So you're going to have to go back and reflect on that. Web work for Friday. Web work for Friday.